spectrum of the labor market. They're down campus-wide 60 janitors. So if anybody here is, you want a job and you have some experience in that particular area. Anyway, so I said, okay, I understand, but I don't, I can live with the boards and I can live with this messy and stuff, that's fine, but please bring some chalk. Please just have somebody drop some chalk off in the room. And here's why. Because my students, they don't listen to me, I told her. I told her, they just write down what I put on the board. But when I talk, they just hear blah, 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 blah. They don't listen to me. So if all I'm doing is talking, then, and if you don't want bridges to be falling down in 20 years, then you better bring some chalk, So anyway, so some chalk appeared, which is nice. And then after I hung up the phone with the janitor lady, I called the IT people because you can hear me better now, right? So I got the microphone on again, and because there's a clip, and the reason there's a clip is that I called the IT people and I explained. I said, "There's no clip on the microphone. I can't use it. I did what am I going to do?" And the guy on the other end says, "Professor, your students don't listen to you anyway, so you don't need the microphone." But anyway, somebody did bring a clip so you can hear me better. And by the way, everybody, I'm just joking. I know you listen to me. Usually. Sometimes. Well, okay, everybody. Thanks for coming on this day before Thanksgiving. I hope you're doing well and you have some nice plans for the holiday weekend. Let's get to it. So we were talking about beam deflections, the second to last topic in the quarter. And so let me just remind you of the central result that we came up with. The picture here. So now I'm finally drawing a beam in a deflected configuration, right? And there is this kind of center line here, and that's this curve that I've just drawn is the line of centroids of all the cross sections. So it's a line that connects one centroid to the next. The x-axis is this way, the y-axis is this way. I'm imagining there's some loading, I don't know, something like that. And what we're after here is the transverse deflection or y-direction deflection of that center line. It's this distance right here. We call it little v. It's a function of span-wise position being given by the x-coordinate along the span. Now I'm grossly exaggerating the amount of deformation here. Okay, so in small deformations rules the day here, everybody. Typically that means if you look at the deformed structure, you can't even see that it's being deformed, right? But nonetheless, there is some deflection, and we often care a lot about what that deflection is, even though it's small. If the structure is statically indeterminate, and we'll get into such situations today, you have no hope of even getting the bending moment distribution, and therefore the stresses, if you don't also solve the deflection problem. So that ought to be front and center in your mind, everybody. If the structure is statically indeterminate, there are too many supports or something, then you can't do anything. You can't get anything, stresses, strains, bending moment, shear force, any of that, without also solving for everything, meaning the deflection problem. All right, so this deflection here is little v as opposed to capital V, which is big V, which is the shear force. All right, so we did derive the so-called moment curvature relationship, which holds that the second derivative of the deflection with respect to x equals the bending moment, which of course may well vary down the length, which it usually does, divided by EI, E being the elastic modulus of the material, I being the second moment of area of the cross-section around the z-axis. The usual I that you know and love. Okay, so this is the so-called moment curvature relation. Or moment curvature equation, I'll call it. We call it that because, well, the bending moment's on the right-hand side, and the second derivative of the deflection, which you could call the curvature of that centroidal axis. That's on the left-hand side. So this offers us this is a little differential equation, right? I mean, if you use statics, let's suppose the beam is statically determinate with its supports. So we can, get the bending moment distribution, right? However complicated the loading is, one can figure out what that bending moment distribution is. And then you just have a little differential equation to integrate, and it's a simple one, right? You just integrate twice, and that gives you the V, and we'll do that a lot today, okay? And that gives you the deflection as a function of X. So this was, this is the main result, that we got from last time. All right, and so we were, I think, right in the middle of an example, a simple example problem. Let me just remind you what that was. We'll finish that off and move on to some others. So here it was, we just had a simply supported beam with a uniformly distributed load. Magnitude F, so the F, of course, it's force per unit length. And we found, I'm just going to pick up where we left off on Monday. We found the bending moment distribution, which is the thing we want if you want to get the deflection, right? You need the bending moment distribution. And we found, of course, that it's this parabola like so. And the functional form was F over 2 times X times L minus X. So there, this is this parabola right here, basically. So notice you actually need the bending moment over the whole span. You need it as a function of X, not just somewhere. Not just the maximum value or something. That's not going to give you the goods if what you're trying to do is get the deflection. Okay, so the next step, so that's where we left off, that's as far as we got. And so the next step then is to integrate. I'm going to use primes here consistently for derivative with respect to X, if you don't mind. So we have V double prime equals M over EI. And so that's just, in this case, F over 2 EI times LX minus X squared. So I just want to solve this differential equation. It's an easy one to solve. Now, I think many of you or most of you have had, or maybe you're in now, the differential equations. Is that 22B? Okay. So I think you at least have to be in it, right? So that or do you have to have already taken it? I can't remember how to correct. Anyway, so you know what a differential equation is, right? It's something like this where there's an unknown, not number, but unknown function in there, and or its derivatives. Right, and this is a simple differential equation because all we have is one appearance of the unknown function. Well, its second derivative. There's no other appearance. There's no like v or something also, which would make the solution more complicated. All right, so it's so simple that you can just repeatedly integrate here. So we're going to integrate once, and that'll give us the first derivative of the deflection with respect to x will be f over 2ei times, well, let's see, this will be L over 2x squared minus x cubed over 3, right? And then plus a constant of integration. Can't forget that. The constant comes out because, look, if you differentiate both sides of this thing with respect to x, then no matter what a is, you get back to what you started with, right? So that means a is arbitrary, at least for the moment. Okay, and then we now integrate another time to get the deflection itself, and we get f over 2ei L over 6 x cubed minus x to the 4th over 12 plus ax plus b. That look okay? So there's the general solution, right, to this differential equation right here. But that's the good news. The bad news is we have this a and b in there. So how does this go, everybody? How do you get these constants? What do we invoke? Yes, please.
Plug in the location of the zeros on the ends of the beam.
Yeah, so there's a word for, there's a general term for what your boundary conditions, right? Okay, so here's a way to look at this, everybody. This differential equation, this governs the behavior of the unknown function on the interior of the domain. The domain is just the x-axis, one-dimensional domain from 0 to L, right? And so inside that domain, so bigger than 0 and less than L, this differential equation governs the deflection. So x here ranges from 0 to L, not including the endpoints. The deflection is known at the endpoints, right? The deflection is 0 there, it's 0 there because of these supports. Those are called boundary conditions. So this always happens in differential equation theory. Okay, the differential equation itself governs the unknown function inside the domain, and then you got to know something about the unknown function at the boundary of the domain. And we do. We know that v at 0 equals v at L equals 0, and these are boundary conditions, so-called. So all you do is you enforce those boundary conditions, and those tell you what your constants of integration are. Okay? So going through that little exercise, so if we enforce v at 0 equals 0, well, let's see, just put in 0 for all the x's there, and you see that, well, that means that b is equal to 0, and then if you now enforce v at L equals 0, well, let's see, that looks like it's going to tell us f L to the 4th over 2ei times 1/12, and then plus a times L equals 0. Yeah? Yes, please. No, all I did was I distributed the x there. Yeah, it just looks a little different, but it's actually the same thing. Yeah. Okay. So, therefore, let's see, a here, this is the constant of integration a, is just going to be minus f L cubed divided by 24 ei. So now we got the a and b, and now it's going to be a simple matter of just putting the a and cycling the a and b back into the general solution, and that'll be the deflection equation, right? So it'll be v. Here's the solution then. V's function of x is f over 2ei, and then that multiplies L over 6 times x cubed minus x over 4 times 12, and then we have the b is 0, and then so then we're going to have minus f is already there, so L cubed over 12, it looks like. And then that can't be, oh, there's an x in there as well. There we go. All right. So there's a general solution here, everybody. Not general, this is the final solution for this simply supported beam with uniformly loaded. And where is it going to be biggest? Where's the deflection going to be biggest? If you really cared about how much this thing is deflecting, that's probably what you'd want to know, right? So it's pretty obvious from symmetry, it's right in the middle. If you don't like that, then just take the derivative of this with respect to x, set it equal to 0. Solve, you'll find that the maximum is at x equals L over 2. And so if you evaluate f at L over 2, you get minus 5 divided by 384 f L to the 4th over ei. So that's the maximum deflection in magnitude, it turns out. All right? So this one's pretty straightforward, I think. you just straight up and down get the bending moment distribution, then integrate it twice, and then set the constants of integration based on the boundary condition. All right, so let's do another one, and this next one is going to involve a little complication. That's the reason for doing it. But now there's no erasers. I guess you could have one but not the other. It's just this one little tiny eraser. I think somebody's messing with me, you know. We'll give them chalk but no eraser or something. Another example, this one will look pretty similar, but there's a crucial difference here. See if you can spot it. So simply support it again, length L, and this time we're going to do this. Not distributed load anymore. Instead, there's a concentrated load in the middle. And that's going to complicate the process of getting the deflection just a little bit, and here's why. Well, you know, again, what we're going to do is integrate twice. V double prime equals m over EI. So we need m. We need the bending moment distribution. So, now I'm not going to bore you to tears here with the calculation of the bending moment distribution. I'm sure you know what it looks like. So I'm just going to draw it. Straight up and straight down, right? Instead of a nice smooth parabola, it's just, you know, this piecewise linear thing, right? Does that look right? Yeah. And the maximum value here is FL over 4. Is that what it turns out to be? That's the maximum value. So here's what complicates things, everybody. You know, we can't write a single expression that covers the whole range from 0 to L for the bending moment. Instead, this bending moment distribution is piecewise defined, right? So in this range from 0 to L over 2, the slope is, well, F over 2, I guess, right? That's the slope. And so in this range right here, we have that the bending moment equals F over 2 times x. So that's good for x in the range 0 to L over 2. And then in this other range here, the slope is minus F over 2. Yeah? And so the bending moment in that range has a different expression. It's linear still, but it's a different expression. It's going to be minus F over 2 times x, and then plus probably FL, right? Does that work? If you put L in there, no, it doesn't work. Yeah, it's FL over 2. So you put L in there, yeah, that works, okay? So we have these two different expressions here. We don't have a single expression, but yet we still want to integrate, you know, V double prime equals M over EI in order to get the deflection. So what do? I mean, you don't have just a single expression on the right-hand side. Instead, what we have is this. We have the following differential equation. V double prime equals F over 2 EI times x, and that's our differential equation that holds in the range 0 to L over 2, and then we have v double prime equals f over 2 EI times L minus x, and that holds for x in the range L over 2 to L. So, I mean, you know, theoretically, in concept, there's no problem here. We have a well-defined right-hand side in the entire range 0 to L. It's just as in a practical matter, it's a little awkward, right? Because we have that right-hand side actually has two different expressions depending on which range you're in. Here. So what do? Well, here's what you do. Here's what you do. You integrate in each range separately, and that's going to bring out two constants of integration for each range, right? So for the range x going from 0 to L over 2, what we get, just integrating that thing twice, the top expression there, that f over 2 EI times x, what you get is v is a function of x. Well, let's see, integrate x once, and that gets x squared over 2, and integrate it again, and that brings you to x cubed over 6, right? So we'll have f over 2 EI times x cubed over 6, and then two constants of integration will have come out from that integration, right? What I've done here is just integrated the top expression there twice. So you integrate once, and then an a comes out, and you integrate again, and then that a turns into ax, and then a b comes out. So you end up with a just general linear when you integrate twice. Is that okay? Okay, so that holds for x in this range here. Now for x in the range L over 2 to L, what you get instead is what happens when you integrate the second right-hand side twice. So we'll have f over 2 EI. Okay, and then integrating L minus x once brings you to Lx minus x squared, and then integrate again, and you get to L times x squared over 2 minus x cubed over 6. And then plus, now I can't say ax plus b, that's the key here, everybody. They're not the same constants. You can't assume they are the same constants. In fact, they're, in general, not the same constants. So we got to write in here cx plus d maybe, right? So now we got these four constants, which sounds like a little bit of a bummer, but what's even worse is that we only have two boundary conditions, right? V is 0 there and V is 0 there, so what gives? So let's at least write down what we do know. We do know that V at 0 is still 0 because of the support at the left end, and V at L equals 0, and that's because of that roller support at the right end. So what now? I mean, we've got these two boundary conditions, but four constants to set. By the way, this is the correct expression to use when enforcing this boundary condition, right? Not this one, because this one doesn't even apply at x equals 0. And this boundary condition is enforced on this second expression here, because, well, this is the expression that holds in that second range, right? But what about the other two constants? Well, you know, we have, fundamentally what we got is we have a deflection over here and a deflection over here, and they can't just be independent, right? I mean, they got to do something where they touch. Don't they? Right at L over 2, don't they have to match? Wouldn't you say? I mean, the beam isn't going like that, well, unless it was that bridge that you see there, you know, picture of the day. So there's the point is, everybody, here's the key. There's a matching condition right where the two right at the interface between the two ranges, right at L over 2. They both apply at L over 2. Right, and what we know is, so this is now matching down here. The matching conditions are that V at just a hair to the left of L over 2. I'm going to call that L over 2 with a little minus sign as a superscript. That means just a hair to the left. That puts us in this range right here. That has got to be equal to V at the same point, but just to the a hair to the right of it. L over 2 with a plus. So that puts us into this range here. So this matching condition is the same thing as saying that at L over 2, at x equals L over 2, this expression has to equal this one at that particular point. So that's a matching condition. So that's great. I think we're all kind of happy with that, but yes, please.
Can you go over why they're slightly adjacent to each other versus why they are matching at exactly L over 2?
Oh, well, so this minus and plus, this really is a hair. I mean, like by hair, it's a mathematical term meaning infinitesimal. So really all this really means is right at L over 2, but use this expression. And all this means is right at L over 2, but use this one. Yeah, sure. So now we have 3, and that's at least a step in the right direction, but we really need 4 conditions, right? Because we have 4 constants, A, B, C, D. Well, we're kind of on a roll with this matching business. So what else matches, do you think, right at the L over 2? What do you think? So the beam doesn't break, so that means the deflection matches. But does it kink there? No, it doesn't kink either because it's got some bending stiffness to it. It's a beam, it's not just a string, right? If you had a string, like a guitar string or something, and you push down on it at a point, just like we're doing here, well, okay, so there's going to be a kink there. But that's only because there's no bending stiffness to a string. This is a beam, so you can't make it kink unless you break it. And there's nothing in this theory that, that accommodates that. So everywhere in the takeaway here, everybody, is everywhere in a beam, no matter what crazy thing you do, you put a concentrated force, you even put a concentrated moment, doesn't matter what you do, the beam's slope stays continuous too. The slope matches as well. So that's going to be the second matching condition here. V prime at L over 2 minus equals V prime at L over 2 plus. So those are the 2 matching conditions and 2 boundary conditions. So that's good. Now we got 4 conditions. That's the happy news. The not as happy news is, what a drag. I mean, 4 constants and these 4, you're going to be at it for a little while, right? With just grinding through the algebra. It's not a real big deal, but takes a little time. So let's just go through these. So this first boundary condition is enforced on that one. So just put in 0 for the x's, and you just get, so this is v at 0 equals 0. This tells us that b is equal to 0. So one of those constant goes away. And then the other one, v at L is 0. Well, that one tells us that you've got to put L in here for all the x's, and then that'll give us an equation that involves c and d. So let's see what we get here. We'll get FL cubed over 2EI. And then what's going to go in here, this will be 1/2 minus a 6, so that's a third. And then plus CL plus D. So that is equal to 0. Okay, so that's 2 down, 2 to go. I just enforced the 2 boundary conditions, and now I got to enforce the 2 matching conditions. So, let's see, enforcing the matching, we have derivative to EI times L cubed over 8 minus L cubed over 48 plus CL over 2 plus D. Ugh. If you're getting the impression that you get in kind of deep if you have to do matching, well, you're right. And so it'd be nice to avoid having to do these matching conditions whenever you can. It's not, you know, it's not like worse than death or something, but it's close. Anyway, but just theoretically here, what do we have? We have B is equal to 0, so that one's gone. Then we have this other second equation there, just involves C and D. Then we have a third one here, it involves A and C. And then this fourth equation has A and C and D, all of them in there, okay? So you got to just solve them simultaneously. And then when you do, here's what you get. And no, I'm not going to stand here and do the algebra in front of you. Instead, I'm just going to read you what I got. Because you know I'll make a mistake, right, if I try to do that. So here's what I got. I got A equals minus FL squared over 16 EI. B is equal to 0 still. C, that one is minus 3 FL squared over 16 EI. And then finally, D, that one is FL cubed over 48 EI. So that's what you get, and then the maximum deflection, of course, is right in the middle, V at L over 2. And of course, it doesn't matter which of the two expressions I use to evaluate at L over 2, because they both match there. We enforce that. So that turns out to be a minus FL cubed over 48 EI. So that's your maximum value right there. All right, so this is an example of this matching condition business, everybody. And you have to do this anywhere something, I'll say, abrupt or discontinuous happens that causes the bending moment to be defined differently, going across that point, right? So here we had a concentrated force, and so that caused the bending moment to switch from a line like this to a line like that. And so we had two different expressions in the two different ranges. We had to do matching at that point. Now, if you had something else like if you had something like this. Now, I'm not going to do this problem, but I'm just going to make a point here. Supposing we had, I don't know, maybe a built-in like that. If you had something like that, well, here again, one single expression for the bending moment doesn't cover the whole range, right? You're going to have one expression that's valid in this range, and then another expression will just be linear. The bending moment will be linear in this range right here. Okay, so there again, you'd have to break the beam right there, integrate this expression twice, integrate this expression twice. Two constants of integration come out in each of those processes, and then you'd have to do matching right there. And again, the matching is going to be the deflection matches, the slopes match. Okay? Now, what if you had this? much, you know? I mean, come on. So you have 1, 2, 3 points where you got to break the beam. The bending moment distribution here is just piecewise linear. So a line, a line, a line, a line. 4 different lines, but they're all different, right? They're different linear expressions. So you'd have to integrate twice, twice, twice. You'd end up with 8 constants of integration in the 4 ranges, right? And you'd have 2 matching conditions at each of these breakpoints and 2 boundary conditions. And, you know, you'd be at it all day, probably. Now, I don't mean to convey to you, everybody, that there's nothing that can be done about this situation. If we had a couple more lectures, I'd probably introduce singularity functions, which is just kind of like this fancy mathematical way of representing broken or piecewise functions with a single expression. We're not going to do that. Instead, what we'll do is superposition. We'll probably get to that by the end of today's meeting, which can help us do problems like this kind of fairly quickly without having to go through this breaking and matching business. But anyway, you ought to know that, you know, in the worst case, if you had all the time in the world and nothing else to do, I mean, imagine you're, I don't know, stranded on a desert island or something, and nobody's coming to rescue you, and all you have is this great big, the tide's gone out, because you have this big expanse of wet sand and a stick, you know? Then you do this, I think. Yeah. Okay. So, let's keep going here. So what we've talked about so far with this beam deflection stuff is the governing differential equation, which is this. So that's the end of that example problem, everybody. The governing differential equation says that the second derivative of the deflection with respect to the span-wise position, x equals m over ei. So in order to use this, you're on the hook for getting the bending moment. Right? And sometimes it's not all that convenient to get the bending moment. And so there's actually another, by the way, so let me just complete this picture here. So this is a differential equation, and then plus boundary, and possibly matching, if you have to, conditions on V and V prime. So that in a nutshell is the math problem that you're on the hook for to solve for the deflection. Okay? It's the differential equation, which is always this. It's always, you know, it's a standard thing. And then what makes one beam and its loading different from another is the boundary conditions and or matching conditions. And again, the matching conditions you have to do wherever something discontinuous happens. There's a concentrated load, there's the end of a distributed load, something that causes the bending moment expression to change as you go across that point, right? So that's the generic situation. Now, what I'm about to introduce to you is another way of approaching that doesn't follow this pattern. It's another way of approaching these beam deflection problems that in some circumstances is quicker, it's more straightforward, it takes less chicken scratch, you know. But I do want to point out one thing here. Notice, everybody, that the matching and boundary conditions, they are at most on the deflection itself and its first derivative. Okay, you don't do matching or boundary conditions on the second derivative or the third derivative. This is kind of basic differential equation theory. Boundary conditions are only on the unknown function up to one order of differentiation lower than the differential equation itself. So if it's a v double prime is lurking in your differential equation, if it's a second order ODE, in other words, then matching and boundary conditions only go up through the first derivative, or else it just doesn't work. Okay? So is there such a thing as a boundary condition on v prime? What would that look like? Like, what kind of support would you need at the end? So that roller right there does not tell us what v prime is, right? V prime is the slope, isn't it? I mean, if you push down on this beam, then sure, the slope's going to be non-zero there, right? Is there some way to make the slope zero there? How about this? Isn't that what that means? A built-in connection there, so-called cantilever beam. You build in the connection, and what this cartoon is right here, what it means is, hey, the deflection is 0 and the slope is 0. There's something holding on to the end and providing a moment reaction which prevents the slope from being other than 0. So that's what that means when you see it. Okay? So we'll do some examples like that as well. It's time to quit for 10 minutes, everybody. Okay, so we'll get to this so-called fourth order method I'll tell you about after the 10-minute break.
Can I charge? Is this working?
And plus boundary and matching conditions as necessary on V and V prime. So that's what's up next. Okay, let's call this the fourth order method. Method here is method of getting beam deflection solutions, right? So we're going to start with what we know, which is that the second derivative of the deflection equals m over EI, bending moment divided by the flexural modulus, so-called. But here's the thing, everybody. We know something else about bending moment. We have these equilibrium equations, right? Remember those? We know that the derivative of the bending moment with respect to x equals the shear force. Notice these little tags on the top of the V here. Shear force, right? That's uppercase V. And more than that, we know that the derivative of the shear force with respect to x equals the distributed load, whatever it is, maybe 0. Right? W is force per unit length. It's positive if it's up by convention. These two things here, these are equilibrium equations, right? This first one's called bending moment equilibrium. The second one's called the shear force equilibrium equation. They always hold if the beam is, well, in equilibrium, right? It's not accelerating. So what's to stop us from, hammering away at this moment curvature relation here? Maybe taking some derivatives of it and see if we can use these in there. So for example, if you were to take the first derivative of, well, you're going to tell let me multiply through by EI here, right? So EI V double prime equals bending moment. Well, what's to stop me from differentiating both sides of that with respect to x? Nothing, right? And then now I've got m prime here instead of just the bending moment, but m prime is equal to the shear force, right? So I've got that so far. And in fact, we're not done getting this fourth order method, but that's actually useful all by itself. That the shear force equals EI V double prime and then prime on the outside of that. So let's keep going here. I mean, what's to stop me then from differentiating again? Nothing, right? So what's to stop me from saying, oh, well, EI V double prime now equals the first derivative of the shear force with respect to x, which after all is equal to just W by shear force equilibrium, yeah? So equals W here. So that's kind of nice, isn't it? It's, oh, by the way, I'm leaving the EI here inside these derivatives in anticipation of applying this stuff to maybe a tapered beam. So if the beam is tapered somehow, then either E or I, probably not E, but I, is going to be a function of x too, isn't it? And so you need to leave it in here. But if I'm just going to tell you that, so if at some point in your future lives you run across a tapered beam, which you probably will, and you want to know its deflection, then you know this is it right here. But for our purposes, our beams are all going to be straight beams, so we can take the EI outside here, and what we're left with is the fourth derivative of the deflection with respect to x equals the distributed load divided by EI. So there is this, at least the differential equation for the fourth order method. The nice thing about it is you don't have to know what the bending moment, you don't have to solve for the bending moment distribution first, right? I mean, this W here, after all, it's part of the load. It is the load on the beam, right? So it's something that you would know just from the problem specification. The bummer about it is that now this is a fourth derivative here, right? So it used to be that we had to integrate twice this thing to get the beam deflection, and two constants would pop out. And now we're having to integrate 4 times, and 4 constants are going to pop out. Right, so it's sort of no free lunch, you know. Pick your poison, I guess. But sometimes this is the better way to go, the easier way to go. And what I'm going to try to do is convey to you when that's the case, when it's probably a quicker thing to integrate this 4 times and deal with those 4 constants, than to first get the bending moment distribution and integrate that twice. Okay, but before we get to those examples, let's talk about boundary conditions. So this fourth order method here merits a fairly elaborate discussion of boundary conditions. Okay, BCs, and I'll put in parentheses here, and matching conditions. But you know what, as a practical matter, you never want to find yourself doing matching with the fourth order method, because then you'd have 4 matching conditions along with 4 boundary conditions. It's just not that practical. Okay, so this is just kind of in theory. So boundary conditions for the fourth order method. Let's try to line up the mathematics with the actual support conditions. Okay, so if you have a built-in support like that, so again, what this means, there is a little cartoon. What it means is that the deflection is 0 and the slope is 0. They're both 0, right? So we're holding on to the end here and not allowing it to go up and down, and we're not allowing that end to rotate either. That's what that means. Now, and I'm drawing all these at the left end, and of course they apply equally well to the right end of the beam. So this roller here, it's the same thing as a pin, right? It said that would be just a different graphical representation of the same thing. You know, this kind of thing means the same thing, a little roller skate like that. Means the same thing, right? It means, hey, no up and down, okay? No displacement in the up and down direction, but no moment reaction there. So this point is allowed to rotate all at once. There's nothing to stop it from rotating or from the slope to change, right? So you can't say anything about V prime here, but what you can say is that V is 0, the deflection is 0. Can you say anything else there, everybody? This is a fourth order method, remember, and so boundary conditions can legitimately involve the solution itself. That's V, V prime, what else? V double prime, V triple prime as well, right? Remember, the boundary conditions can go up to 1 derivative order less than the differential equation. That's legitimate. So do we have any of those higher derivative boundary conditions here? What else can you say here? Remember, with boundary conditions, everybody, what you do not see is just as important as what you do see. And what you don't see here is any moment there. I'm not, applying a moment. There's no support condition like this and this one that would cause a moment reaction. In other words, the moment there is zero, is it not? The bending moment is zero there. Do you all get that? Okay, so if the bending moment is zero, well, after all, m equals what? EI times V double prime. That's true everywhere in the beam, right? M equals EI V double prime. So if m is zero here, the bending moment is zero, then that means that the second derivative is zero there. And that's a legitimate boundary condition on this fourth order method. It's not okay for this second order method, but you'd have to leave that off. But this is totally legitimate for the fourth order method, okay? All right? All right, well, let's see, what else could you have? You could have this. You could just have, flapping in the breeze like that, no support at all. You cantilever or something. So what's going on there? Well, there's no support. We can't say anything about V itself. We can't say anything about the deflection. That's going to be part of the solution. We can't say anything about the slope. Right? If you're pushing down on the beam over here somewhere, then there's going to be some non-zero slope there. That's part of the solution too. What about the bending moment at that end? Big fat goose egg, right? You don't see a moment applied there, do you? So here we'd have that the bending moment is zero, and therefore the second derivative is zero. Oh, by the way, everybody, if there were an applied moment there, then it wouldn't be that the moment is zero, but it would be instead that the moment is whatever the applied moment is, right? Whatever you're applying there, right? So the boundary condition in that case wouldn't be V double prime is zero, but instead it would be V double prime equals the applied moment divided by EI rather than zero, but still known. What else do you not see there? Well, you don't see a force, at least in my picture. So that means there's no shear force there, right? There's no big V. And if there's no shear force, what does it tell you about the deflection? Well, it's lurking on the board up there, so right there. So what does it say about the deflection? Something fancy about the deflection. Third derivative is zero, right? The third derivative is zero, and that is because the shear force everywhere equals EIV triple prime, just as the bending moment everywhere is EIV double prime, the shear force everywhere is EIV triple prime, including at the ends. So if you know big V at the end, you know V triple prime at the end. And again, if instead of this, well, in fact, let me just include it as another case. Supposing we had just a cantilever with a tip load. So no moment here, right? There's no moment there. So that means the second derivative is zero right at the end. But there is a shear force, right? What is it? Isn't it just P? Yeah? And if the P were up, then the shear force would be minus P, but I've drawn the arrow down. So V is equal to P, big V is equal to P there. So that means the third derivative of the deflection is going to be equal to P over EI. And by the way, hopefully this is obvious to everybody, but it doesn't hurt to say it. Everywhere you see here, I'm talking about boundary conditions. At the end of the day, there's some condition on V or V prime or V double prime or V triple prime. All of these things mean evaluated at that point, right? So this one should really say, V at zero equals zero. V prime at zero equals zero. So I haven't included explicitly the point of evaluation, but hopefully that's clear. That these conditions, all of them that I'm writing here, all of these, they all mean evaluated right at that end point. at L or 0 or whatever it is, okay? That good? Okay, so that's what I want to say about boundary conditions for the immediate moment. Probably before we quit today, the plot will thicken a little bit. We'll introduce some kind of more fancy boundary conditions, okay? You'll see what's fancy about them. But just a little teaser there, everybody. You know, this kind of thing, built-in connection there where we're saying deflection is 0, slope is 0. That's a totally rigid boundary condition. That means that whatever is over here is so stiff that, you know, no matter what force is required to cause the deflection to be 0, then this support is capable of providing that without budging at all. You know, whatever moment is required there to cause the end to not rotate at all, again, that happens too. But that would be, you know, kind of an impossibility in the real world, right? Instead, there's always going to be some finite stiffness there, right? And so these are idealizations, but often you have to take that finite stiffness of a support into account. And so that's what I mean by fancy boundary conditions. So we'll get to that in a little bit, but let's do an example problem right now. And this will be a statically indeterminate example problem. So this will be one where even if all we wanted to know is the support reactions or maybe the bending moment distribution, if that's all we wanted to know, you know, statics stuff, we would not be able to get those things without solving the beam deflection problem. And if some on your homework, I distributed the homework 9, the very last one, yesterday, okay? So please have a look at that. You know, you probably want to maybe do a little bit every day or something. It's due in a long time. It's due a week from Friday. So the 3rd of December at midnight is when it's due, and that's the last day of instruction. Oh, by the way, I'm trying to find a big enough room to have a little, we'll call it review session or something. And I asked the registrar if we could do it Monday of finals week, that's the 6th, and the registrar said no. No is what I heard. And I said, why? And the registrar said, well, because it's finals week. And I said, so what? And they still said no. So we probably get the impression I'm on the phone complaining to people, different people in the university all day long, right? You know, I'm actually, I think, pretty easygoing guy. But anyway, so that's what the registrar told me. And so we're going to do it Friday, all right? So 4 to 6 p.m., Friday the 3rd. Okay. But anyway, so I'll send out an announcement about that when I get the room nailed down. So here's another example problem, everybody. Cantilever, but a propped, what's called a propped cantilever beam. So rather than just sticking out of the wall like this, there's also a support here. And let's make it the load uniformly distributed like that. And the length will be L, and the flexural modulus is EI. Now, can you eyeball this, everybody, and convince yourself it's statically indeterminate? Take away that support right there. Did the thing fall down? Nope. Statically indeterminate then, right? Or if you release the moment reaction there and convert this built-in into just a pin or a roller, it still doesn't fall down, right? So if you, in other words, if you release one of the reactions, it doesn't fall down. So it's statically indeterminate. So another manifestation of the indeterminacy is that if that roller there isn't put in just exactly the right place, think about that. If there's a little gap in there, even if it's small, it's too small to see. If there's a little gap there, then you're having to push down some amount before you even close the gap, right? And so that little tiny gap is going to actually change the bending moment. It's certainly going to change the reaction there a lot. And it will therefore change the bending moment distribution and the stresses and everything. And so this is I was talking about earlier with the manifestation of, a manifestation of indeterminacy, or an attribute of indeterminacy, is that if the geometry isn't quite right, the support isn't quite in the right spot, or something isn't quite the right length, it just radically changes the stresses throughout the structure. Okay, but anyway, let's get support reactions. Let's see. So there's going to be a force there and a moment reaction there, and there's going to be a force there. And if this were just roller instead of built-in and roller, then we'd have two force reactions and that's it, right? And would they be equal by symmetry? You betcha, they would just be FL over 2 and FL over 2, right? Now, because we have this built in here, do you think that's going to offload or offload this support here, or cause it to have a larger reaction? Is it still going to be FL over 2, or bigger than, or smaller than that? What do you think? I have a vote for smaller. Who says the force there is going to be less than FL over 2? You're looking around. You're like, before you put your hand up, you're like, let's see what everybody else. Yeah. All right. So, and who says small? Who says bigger? So the fact that there's this support, built-in support, that's going to make the reaction there bigger than FL over 2. Okay. Good. Yeah. You're wrong, but I mean that's you had, conviction. That's good. Sorry, man. I don't mean to pick on you. But anyway, let's do the analysis and see what happens. All right. I don't think it's necessarily intuitively obvious, but let's do the analysis and see what happens. So, what we could do is we could use the second order method, but what would that mean? That would mean, getting the bending moment distribution, and we don't know what that is. There's no way to know because we don't know what that reaction there is, right? We could take that as a redundant reaction and pretend that it's a concentrated applied force, call it R or something, and then that would appear in the bending moment distribution. Okay, we could do that, or we could use the fourth order method, which would be nice here, right? Because we do have a distributed load. We don't have to get the bending moment distribution first. So let's use the fourth order method. So here it is. It's going to be the fourth derivative of the deflection with respect to x equals minus f divided by EI. And is everybody cool with that minus sign? W is what goes here. W over EI goes here, but W is positive if it's up by convention, and my F here is down, or my load here is down, and I've labeled it with F. Okay? So, and you're going to quickly get to the point where you can do this, everybody. Just integrate this 4 times in your head. Okay? Let's not go through this plotting one after another. Just, integrate it 4 times in your head. What do you get? Well, there's a constant here. It goes from the constant to x. Was that funny? Integrating 4 times in your head? It's not that bad, really. It goes like this. So the constant goes to constant times x, then constant times x squared over 2, then constant times x cubed over 6, then constant times x to the 4th over 24. All right, so that's what the constant term turns into. It's going to be minus f over 24 EI times x to the 4th. And then what else happens? Well, a general cubic is going to come out, right? 4 constants of integration. So a polynomial with 4 unknown constants. Each one is a constant of integration, comes out. ax cubed plus bx squared plus cx plus d. Okay, so that's a general cubic. You got to slap on the end there because of this integrating 4 times. Now, if you did go the plotting way and integrate once and then another time and so on, then you would have ultimately had like a over 6 here and b over 2 there, right? But is a over 6 and a, does it matter? A is just as good a constant as a over 6, right? B over 2 and b, just be a different value in the end, but they're just one is as good as the other. So just write the general cubic there. Now we need boundary conditions because we've got to nail down these 4 constants. So let's get the boundary conditions. So at the left end, what do we got? We have v at 0 is 0, right? These are the BCs here. So deflection is 0 there. Slope is 0 there, right? What else? Well, at the right end, what do we have? Zero deflection there, right? V at L equals 0. And what else is 0 at the right end, everybody? What you don't see is just as important as what you do see, and what do you not see there? You see a roller which will make a force, but you don't see a moment there, right? Yeah, so the moment is 0 there, so what does that tell you about the deflection? Its second derivative is 0, right? So is both the deflection itself and the second derivative is 0. And this last one is because m at L is 0. Oh, it just popped into my head. I was also going to say that maybe we'll have a little office hour at 2 o'clock this afternoon or something, because, you know, there's going to be no office hours Thursday and Friday, and I'm going to miss you guys. I am actually. But anyway, there's no office hours Thursday and Friday. So why don't we maybe have one this afternoon if anybody's around and wants to come around? 2 o'clock, is that okay? I'll send out an announcement when I get back from. Yes? Oh, that wouldn't be good, would it? Yeah, that may be true. Yeah, that's probably true. So let's see who that is. Today's Wednesday. Oh, Zai Lau, his office hour is 1 to 2 today. So I'll take over after that. Is that all right? All right. Okay, everybody, so, you know, we're in a good spot here, right? I mean, we've got these 4 constants of integration, we have these 4 boundary conditions. I would really urge you to pay a lot of attention to the boundary conditions, because this is where things can go off the rails, right? This, writing down the boundary conditions, is really where the engineering is. I mean, the differential equation itself, that's kind of a stock thing. Integrating 4 times, that's just a little bit of tawdry mathematics. But then the boundary conditions is the engineering. It's looking at the physical scenario and translating it into the math. That's fundamentally what engineering, a lot of it, what it's about. So get here and have confidence in that. And once you do, then it's time to go on and just, you know, do the algebra. Not a whole lot to it. But basically what you're doing is trying to solve for the ABCD by enforcing those boundary conditions. So, let's just do that. So V at 0 is 0. Well, that one just tells us that D is equal to 0, right? That last constant there is 0. And then V prime at 0 equals 0. Well, that tells us if you just differentiate your deflection there with respect to x, that leaves a c on the end, and just a constant c, and evaluate at x equals 0, and then, you know, all that's left there is just c. Of course, so we have that. So 2 of them are gone. That's pretty nice so far. And then let's see what else we have. We have the deflection itself at L is 0. So we'll have minus FL to the 4th over 24 EI. And then plus AL cubed plus BL squared equals 0. So there's one equation that involves these 2 constants, A and B. And then the last one will be the second derivative of the deflection is 0 at L. And so let's see, that gives us minus FL squared over 2 EI. And then plus 6AL. And then plus 2B equals 0. All right, so look at what we have here, everybody. C and D are 0, and then we have these 2 equations right here. in two simultaneous equations involving the two unknown constants A and B. So just a little tiny bit of algebra to flip that system around and get A and B. And when you do that, what you get is what you get for A is minus 6FL divided by EI. And what you get for B is, and so, wait a minute. Oh, hell. No, sorry. That's for a different problem. Instead, you get something, and I didn't actually write it down. But what I did write down is what you, sorry about this, everybody. What I did write down instead is what the support reactions are. But let's talk a little bit about how would you recover the support reactions. I mean, assuming that you had more patience than I do at this particular moment, and you solved for A and B, so you would, get A and B, and then once you got A and B, now you have a whole deflection, right? So there it is up there, C and D are gone, those are both zero, and you'd have A and B, both of them would be proportional to little f, fine, so you would have the full deflection. So how would you get the support reactions then? Is that worth considering? What do you think? Well, here's the thing, everybody. This is a kind of an important element of the whole process. Once you have the deflection, you know everything about this beam. Not only do you know the deflected shape, but you can easily recover the bending moment. How? Well, m equals EI V double prime everywhere, right? So if you have V, just hit it twice with differentiation, slap an EI on it, you've got yourself the bending moment everywhere in the beam. If you want the shear force, hit it again, differentiate again. Right, put an EI on it. Now you got the shear force. And if you have the shear force, can you figure out what the tip force is? Yeah, sure you can. So, this is the support condition you have at the right end. This R right here, let's call it. We have this downward distributed load, right? So isn't this R here just the negative of the shear force at L? If there's a non-zero shear force here, a positive shear force, then it's down. So if R is positive up, then it's equal to the negative of the shear force there, right? And so that's just equal to minus EI V triple prime at L. So once you have the deflection, that's the main message I want to convey. Once you have the deflection, you're golden. I mean, that's the gold standard of information for this beam. You can get anything you want from the deflection. You can get the bending moment, you can get the shear force, you can figure out what the moment and or forces are at the ends by evaluating the bending moment or the shear force at the ends. Okay? And so when you do this, again, we've got A and B, put them back in there. That tells you what the deflection is. Take 3 derivatives of it, hit it with a minus EI, evaluate at L, and here's what you get. You get R equals 3/8 FL. That's what you get. So it's a little less than half FL. So the fact that you have a built-in support at the left end tends to, or contributes to offloading that support at the right-hand end. And so that means the force reaction at the left-hand end will be 5/8 FL, right? So you have 5/8 over here and 3/8 over there. And then, of course, there'll be a moment reaction at the left-hand end. If you really wanted that, well, just take, well, so here. In fact, let me do a complete job of this, everybody. So we have, and maybe I'll call this one P and this one R. And then there's also a moment reaction here. And you mind if I draw it in the direction it's really going to go? It's going to be that way. And I'll just label that maybe M sub 0. And here is that distributed load. So we already got the R. So the R here, we're just, this is a complete catalog here. So R is going to be minus the shear force at L. And then P is going to be what? Shear force at 0 or minus the shear force at 0? Well, if there's a shear force over here that's positive, big V is positive there, then it is up, right? Not down, but up, because that's a negative X phase. Right? And so the P here would just be the shear force without a minus sign at 0. And then this M0, this support reaction there, well, if there's a moment there, a non-zero bending moment, sorry, a positive bending moment, it would go the other way, wouldn't it? It would poke into the board. So M naught here is going to be minus the bending moment evaluated at 0. Okay, and so all these things, the shear force, the bending moment, you can get those easily once you have the deflection. That's not integrating, that's differentiating, that's easy. All right? Okay, so that's that one, everybody. And now I want to spend maybe the rest of the, well, close to the rest of the time we have today to talk about the fancy boundary conditions that I briefly mentioned. So when I say fancy, really what I mean is boundary conditions with finite stiffness. Is this okay, everybody? Is everybody cool with this example problem? Or is there any question about it? Yes, please.
Please repeat why P equals to positive.
This one right here? Okay, so the reasoning goes like this. So we're right here, yeah? So here's generically, here is the x-axis, that is a negative x face of this beam, right? Because the outward normal to it is in the negative x direction. So on such a face, the sign convention was that the shear force is positive if it points up. Right? Okay. And so looking at my picture here, I've got this up arrow that I've labeled P, which means what? It means that if P is a positive number, there's really a force that's up there. Okay? And so if P is positive for an up force, well, V there is positive if the shear force is up, and those two arrows are the same thing. That good? All right. Okay, so fancy boundary conditions, or finite stiffness boundary conditions, it's really what I mean to say is what's next up. Spring boundary conditions, everybody. Well, let's say spring support conditions. So it is often the case that, as an example, instead of, well, let's just use that last example problem, maybe as something like it as a means of explaining this. Instead of this, which means what? I'm focusing now on the support on the right-hand end. Instead of that, which really means an infinitely stiff support there, no matter how much the reaction force, that point doesn't move at all, period, just, doesn't budge. It is often the case that what you have to do is, rather than that idealization, you actually have to include some finite stiffness in that support. So what I've done here is I've replaced that pin or roller support with a spring. with a linear spring. That's what this thing is meant to represent here. Okay, so what is it? Well, this is some element that, if you push on it, then it pushes back, but it also deflects. If you push twice as hard, it deflects, twice as much, and so on. It's a linear spring. So the force that this spring exerts is proportional to the deflection. That's the key here. So this is one manifestation of a spring or finite stiffness support condition. And you can recover this situation just by making the spring stiffness go to infinity, right? Couldn't you? You can just, jack up the stiffness here to the point where the spring doesn't move, it doesn't deflect at all, no matter how much force is in it. But it is often the case in engineering calculations, everybody, that you've got to take into account the finite stiffness. So what do? So in this scenario right here, what would the boundary conditions be? Well, this is only the case for the fourth order method, right? Because the boundary conditions are necessarily going to involve the third derivative of the deflection, that is to say the shear force. Right, so here's what you do when you're faced with a spring boundary condition, everybody. And I would urge you to always do this the moment you see a spring. Draw draw the end of the supported end in a deflected configuration. And even if you know this point moves down, draw it in an upward deflected, so that the little v is positive. So come off to the side here and draw it like that. So this is just supposing it moves up for whatever reason. What does this spring do if this endpoint, this supported endpoint, moves up? Well, the spring's going to try to pull it down, right? So there's going to be a spring force like that, a restoring force. It tries to pull that point back to zero deflection. Everybody follow me so far? Right? And what is the magnitude of that force? Well, it comes from a spring. It's a linear spring. So the magnitude of that force is going to be the spring constant times the deflection. And what's the deflection? Well, the deflection here of the spring is whatever the deflection of the beam is at that point. You agree? So the label on this arrow then, the amount of this force, should just be the spring constant times the deflection of the beam there. And so, if this little v is positive, as my picture shows, the force is really going to be down. And if there is a downward force there, then that's a shear force, right? And is that shear force big V, is it positive or negative? So if there's really a shear force that goes that way right there, is big V positive or negative? Positive, right? So the spring provides the shear force. And this is the value of drawing the thing in an upward deflected shape, because then you know this is positive, and you don't have to scratch your head at the end. Do I need to put a minus sign in front of it? All right, but we're not done yet, because we know how the shear force relates to the deflection itself. And at the end of the day, our boundary condition has to involve just the deflection itself and its derivatives, right? So what is the relationship between the shear force and the deflection? Wasn't that just EI V triple prime? Little v triple prime, right? Deflection, third derivative of the deflection. Isn't that the case? So there's my boundary condition, everybody. It's that equals that. So the boundary condition here is K, that's the spring stiffness, times the deflection equals EI times the third derivative of the deflection. So that I would call a fancy boundary condition. Looks pretty fancy, don't you think? But, fundamentally, it's just a boundary condition. If you have your general solution, you'd be enforcing this after getting your general solution for the deflection. That is, after integrating 4 times, if you're using the fourth order method. Okay, and so then you'd have 4 constants of integration, an ABCD kind of a thing, like we did, in the previous example. And, you're just going to put that general solution in there, and you're going to put it in there, And, don't run out of gas, everybody. I mean, it takes some perseverance, okay? But just push through the algebra. That's all it is at this point. Get to the boundary condition, make sure you have confidence in them, and then just do the algebra. So you'll have constants appearing on both sides. It'll just be another algebraic equation for the constants. Well, what else is going on here? If there's no moment, reaction, or applied moment, then the other thing we have, of course, is just the moment at L equals 0. And therefore, the second derivative is 0. So those would be your two boundary conditions for this situation right here. A spring, a linear spring, and otherwise nothing else. I mean, no moment. Okay, so that is one type of spring boundary condition. And there's another one I want to talk about in the last 5 minutes here. So everybody, I can't emphasize this enough. I'm pleading with you. Go through this analysis every time you meet a spring boundary condition. Because I'll tell you, if there is a spring on the other end, okay, then it could be different. There could be a sign change in there. All right, so go through the analysis. Draw the thing in the deflected shape. Show the spring trying to pull it down. Just go through it. It's just 2 minutes out of your life, and it's well worth it. So the other kind of spring boundary condition is one that doesn't provide a restoring force, but instead a restoring moment. So let's say, and just for variety's sake here, let's put this at the left-hand end. Let's suppose you had this, just by way of example. So again, a beam extends to the right, there's some loading, there's some other support out there, whatever's going on. But we have a pin right here, but this isn't just totally unrestrained rotation. Instead, there's this kind of, so this spiral that I just drew, what I mean by that is a moment spring. It's like the spring in a wristwatch. Well, a real one, not an electronic, wristwatch. Everybody good with this? So this is a thing which provides a restoring moment. So if this end tries to rotate, this spiral spring pushes it back. Okay, and let's say that spring constant is C. That is the constant between the angle of rotation and the restoring moment. So what you do to work out the boundary condition here is that you would, again, draw the thing, come off to the side, and draw it in an exaggerated deflected shape like that. So here the slope is positive, right? Strictly positive, right? V prime is positive here, isn't it? And what's going to happen if this end tries to rotate in the fashion I'm showing? Well, this moment spring is going to push it back. It's going to try to restore the thing to no slope at all. That's what a moment spring does. And this restoring moment here is going to be proportional to this angle right here. Let's just call that theta. So this moment that I've drawn here, this is a restoring moment. That's the direction the moment's really going to go to push the end back. That restoring moment is going to have magnitude spring constant C times that angle of rotation, theta. Is this okay so far? All right, so is this, if there's a moment like this, is this a positive bending moment or a negative bending moment on this negative x phase? Well, it's poking back into the board, but it's a negative x phase, so it's a positive bending moment, actually. Yeah, so what we see here is this. M at 0, let's say this is at x equals 0. Okay? At m at 0, what we have, the bending moment at 0 is c times theta. But theta, theta, this angle, well, it's about the same thing as tangent of the angle, isn't it, right? Because, it's a small angle, and tangent of this angle is the same thing as the slope of this line right here, which is just v prime, little v prime. So this is just c times little v prime, isn't it? But the bending moment, well, that's, everywhere in the beam, including at the ends. Isn't that just v double prime? So there you have another fancy boundary condition. C, this moment spring constant times the deflection, or the slope equals EI times the second derivative of the deflection. So that's what you get for a moment spring like that. And of course the other boundary condition here would just be that the deflection itself is 0. So there would be your two boundary conditions for a support like that. It's a pin and a finite stiffness moment support. So in the event, or in the limit as C goes to infinity, what you'd really be getting is just this, right? Just built in. So this is the C goes to infinity case. Infinite stiffness there. Time for me to stop yakking. All right, everybody. Happy Thanksgiving. Have a restful and safe, please. Safe if you're traveling. Holiday weekend. Office hour today at 2 if you're around. Otherwise, see you Monday.
This is yours. Thank you.